Good morning, and I want to thank Dr. Patana and the A4M for inviting me to present again this year. It looks like mine's the last presentation before lunch, and so this is an appropriate topic that we're going to look at right now, because we're going to look at mitochondrial bioenergetics and their role in the aging process. And I do want to mention that it's really good to see this transformation at A4M from a predominantly aesthetic, cosmetic, appearance medicine approach to a more physiological and cellular approach, because, you know, really this is the key to age management, because aging begins within the cell. I thought we'd begin with a little overview and a definition, a scientific definition of aging. And so aging has been described as a biological process characterized by cellular decline in energy, a progressive loss of physiological integrity with an attenuated ability to respond to increasing oxidative stress, functional decline, making us vulnerable to disease and eventual death. And this begs the question, well, what is the cause of aging? And I don't think there is any one cause, but this question has definitely caused a framework by scientists that's being generated to look at this question. And they came up with a framework called the hallmarks of aging, and there are 9 hallmarks. Actually, there are 10, because they have now added inflammation to this. And what these hallmarks do is they really outline the cellular disturbances that propagate and promote cellular senescence. But mitochondrial dysfunction continues to grow in evidence and the data to show that it is the main hallmark in aging. And even the scientists now have to agree that mitochondrial dysfunction is the singular universal event that is intimately connected to the aging process. And this really echoes the mitochondrial theory of free radical theory of aging, which was presented by Denham back in 1972. And so many researchers and scientists now regard the mitochondria as the sentinel organelle of the cell. It's the first to detect and the first to respond to any events that occur within the cell, which makes sense, right? Because any kind of activity, any kind of event that occurs within a cell requires ATP energy, so it requires the mitochondria. And the mitochondria is in continuous real-time communication with the nucleus and other cellular components. And it's well documented that as we age, the number of mitochondria decreases. And Connolly and his group in the University of Seattle estimated that between the ages of 38 and 68, there's a 50% loss of mitochondria. Quite profound. And when you consider that the number of mitochondria that we have is directly proportional to the ATP that is made, which is directly proportional to our energy levels. And that correlates with both our physical and mental performance. And as everyone in this room can say that, we cannot run as fast or as far as we could when we were in our 20s. We can't stay up late at night and study and retain and recall like we did when we were in university. Even professional athletes, no matter how hard they train, they can't sustain their optimal performance. They see their numbers, their timing, their performance start to drop off. And this is due to diminishing mitochondria function, efficiency, and a reduction in the number of numbers. Now, fortunately, over the last decade, we've had some incredible advances in science and technology. And researchers have discovered over 270 new variations of mitochondrial myopathies. And while they were doing this, they uncovered and discovered that in the process of making ATP energy, that there are some zones of malleability that can be modified and manipulated to increase ATP production and improve mitochondrial function. And before we get to these zones, I thought we'd just refresh ourselves on how the mitochondria function and make ATP energy. So if you remember, the Krebs cycle occurs within the mitochondria, and the whole role of the Krebs cycle is to produce high energy reducing equivalents in the form of NADH, which supplies the electrons and the protons to the electron transport chain. And the major portion of ATP is made by the electron transport chain. And the electron transport chain is located on the inner mitochondrial membrane, and it's composed of several complexes along which the electrons will travel. And right here, a complex 1, this is where NAD, which is being supplied by the Krebs cycle, will be oxidized and donate an electron to travel along the complex. At the same time, it gives up a proton, or a hydrogen ion, which will translocate across the inner mitochondrial membrane and accumulate in a gradient, forming a proton motive force. And this force actually turns the turbine here to phosphorylate ADP into ATP. Now, it's at complex 4 where oxygen receives electrons and combines with hydrogen to form water. And I just want to point out that this is the area in our body, in the mitochondria. This is the whole goal, the whole purpose of 99% of the oxygen that enters your body. Its whole purpose is to arrive right here, so as to drive the production to make ATP. And it is the oxygen that is taken up by the mitochondria that drives the pace of ATP production. And this whole process is known as oxidative phosphorylation, and it's a very coordinated sequence, and we call that coupling. And when any one of these sequences becomes disturbed, it's called uncoupling, and we get a reduction in ATP. Now, as you remember, during the process of manufacturing ATP, reactive oxygen species, or Ross-free radicals, are also generated as waste byproducts. It's just the cost of doing business. And so part of making ATP is conversion of oxygen into Ross-free radicals. About 2% of the oxygen that enters the mitochondria is converted into Ross. And as we age and the mitochondria become less efficient, the amount of Ross that is generated increases dramatically. It's really significantly. And as we all know, Ross-free radicals love to attack lipid membranes, the mitochondrial DNA, and other proteins. Another point that I want to point out to you is the greatest source of Ross that's encountered by our bodies come from this process, okay? So I know we have exogenous sources of Ross, ultraviolet radiation, chemotherapy, medicines, food, the environment, et cetera, but the greatest amount of Ross that our body will encounter during our lifetime comes from our own mitochondria, and this speeds up as we age. Now, the mitochondrial membrane, just like all membranes, has an electrical potential, and that potential is to maintain the integrity or the seal of the mitochondrial membrane, okay? So as to prevent the leakage of the contents of the mitochondria out into the cell. And with aging, this increase in Ross lowers this mitochondrial potential, and it stimulates specialized pores known as permeability transition pores to open up, spill its contents out, and trigger apoptosis. And this increases with frequency and consequences along with aging. So if you remember back to my first slide, which was a definition of aging, was really kind of a bird's eye view. And now we're really zoning into the subcellular levels for a definition. Maybe not a definition, but a description of how aging is associated with mitochondria. And aging is associated, as we've just seen, with a reduction of the mitochondria population by 50% before you're 68. It's associated with a reduction in oxidative phosphorylation, which correlates with a reduction in ATP. There's increased uncoupling, and there's a loss in the membrane redox potential, leading to apoptosis. At the same time, aging is associated with a reduction in the ability of the mitochondria to replace themselves. And here's a really cool photograph to show you what we're talking about. So in this right upper corner, we're seeing some normal shape, function, mitochondria. And down here, now they begin to swell and become dysmorphic as the membrane potential breaks down, and then all hell breaks loose on the left. The transitional pores open up and just spew out their contents. And this is basically mitochondrial dysfunction and leading to cell apoptosis. Now, I'd like to stay with this theme of membranes, and especially the inner mitochondrial membrane, because there's a component on the inner mitochondrial membrane known as cardiolipin. And cardiolipin is a glycerophospholipid. It is found exclusively, only in the inner mitochondrial membrane. And it makes up about 30 to 35% of the total phospholipid volume. And the role of cardiolipin is to anchor down these complexes, anchor them down into structures known as supercomplexes. And what this does, it provides stability to the membrane structure. It reduces the distance for the traveling of substrates, diffusion of substrates, and improves the electron flux. So it basically lowers the cost of making ATP. Cardiolipin is also responsible for holding onto cytochrome C. This is a key electron transporter, okay? And so the cardiolipin is pivotal, absolutely critical for mitochondrial function and ATP production. Now, because of its proximity to the area for the Roche generation, which occurs in the electron transport chain, the cardiolipin is very vulnerable to oxidation. And when it is oxidized, it loses its ability to hold on to this supercomplex formation, and it loses its grip of cytochrome C. And when this happens, ATP production stops. It's all done, it's all over. And now the oxidized cardiolipin, represented by these yellow structures, and the free cytochrome C stimulates these permeability pores to open up and spill out the contents of the mitochondria. And this leads to apoptosis and cell death. This has become a very highly focused area in the last 5 years because they're now saying that this mitochondrial pore transport system is really maybe a window to the aging process. And so it's gained a lot of attention in both aging and in disease initiation. So how do we slow down this process of mitochondrial delay? And if you remember, I said that these scientists have uncovered some zones of malleability that can be modified and manipulated to increase ATP production and improve mitochondrial function. So let's look at some of the alternatives that we have and some of the tools. And the first one involves a pharmaceutical drug, okay, a lamipretide, formerly known as SS31, named after the doctors who invented it, Setso and Schiller. And the lamipretide is the first drug that is FDA orphan drug designation for the treatment of primary mitochondrial myopathies. There are no drugs to treat any of the mitochondrialopathies, and even this is only in the orphan stage. But because of the success of its early clinical trials, it's really become a very hot new topic. And I'll give you an example of one of the clinical trials. In one clinical trial, there was a group of individuals who could only walk 20 meters within a time frame of 6 minutes. And after 5 days of a lamipretide, they were able to walk 65 meters in the same 6 minutes. Now, I know you're not going to get a gold medal for that. However, this really is a milestone in the treatment of these types of mitochondrial diseases. And its mechanism of action is that it binds to cardiolipin. It binds to cardiolipin, and it prevents the destruction of the complexes. So it maintains the supercomplex formation, and it prevents the release of cytochrome C. And now this allows the electrons to proceed along the chain and ATP production to continue. Because of the success of this drug is now being trialed in multiple other medical models: Huntington's disease, Parkinson's disease, ischemia-reperfusion injuries, which is cardiac arrest, and stroke. And this is because these diseases are heavily impacted by mitochondrial dysfunction. And so this drug has become really exemplifies an area of malleability that can be manipulated to salvage mitochondrial function. You're going to hear a lot more about lamipretide in the next couple of years because it's a paradigm shift on how we're treating diseases. A natural, non-pharmaceutical alternative is natural astaxanthin. Natural astaxanthin is a powerful antioxidant with a very unique molecular structure that allows it to penetrate membranes, phospholipid membranes, and it aligns itself in a very interesting way. And it aligns itself this way in order to maximize its ability to capture and scavenging reactive oxygen species. So astaxanthin is a mitotrophic antioxidant. And I know this is a busy slide, but it gives you an idea. It illustrates how Astaxanthin interferes with reactive oxygen species pathways before they can inflict damage to the mitochondria. Studies have shown that astaxanthin quenches more free radicals than most other antioxidants. In head-to-head studies, comparative studies, astaxanthin was 800 times stronger than CoQ10, 500 times stronger than vitamin E, 6,000 times stronger than ascorbate, vitamin C, in quenching and scavenging singlet oxygen reactive oxygen species. Astaxanthin has been shown to safeguard the redox potential of the membrane potential, so it maintains those transition pores closed. It's been shown to inhibit lipid peroxidation, and it protects the enzymes of the transport channels to fats coming in, carnitine palmitoyl transferase. It's also been shown to enhance PGC1 alpha. Now, PGC1 alpha is the master regulator that controls mitochondrial biosynthesis. In a recent study that was published last year in the Medical Science and Exercise and Sports, in a group of seniors who were already diagnosed with physical decline and sarcopenia, who took astaxanthin for 90 days, had an improvement in their strength of 15% and an improvement in their endurance of 45% and a preservation of their muscle mass. Now, the reason I say this is the sarcopenia, as we age, we lose our muscle mass. And the importance of this is that the major portion of the mitochondria in our body are in our muscles. We have 10,000 mitochondria per muscle cell. So it is the greatest reservoir of mitochondria in our body. And so this study indicated that astaxanthin was able to preserve the activity of the mitochondria, so it improved their energy, their strength, and also preserve their ability to not lose or be converted into sarcopenia and lose muscle mass. Nicotinamide. Nicotinamide, this is a B vitamin. It's gained a lot of activity and a lot of attention lately because it's associated or has a relationship with sirtuins, and those sirtuins, remember, are linked to longevity. Nicotinamide is a precursor to NAD and NADH. Remember, they're the substrates that provide the high-energy electrons and protons to the electron transport chain. Nicotinamide is a prerequisite for sirtuins. Now, these sirtuins are a family of proteins that regulate gene expression, including telomerase. All right, telomerase. And the telomerase protects and preserves the telomere length and advances the Hayflick limit. In other words, it prolongs cellular lifespan. And nicotinamide has also been shown to rescue aging mitochondria. This is because as we age, the levels of NAD drop down. And this is because now the NAD is consumed by other biological molecules who are involved in the repair process. So there's a shift, and there's competition now between the repair molecules and the sirtuins. The repair molecules being PRP, and that's their response to DNA damage and oxidative stress. And as you can see in this diagram, on the left side we have a young mitochondria, and on the right we have an elderly mitochondria, and on the left there's NAD. And so the NAD will now activate the sirtuin to do its job, and that preserves the permeability transport chain pore wide, nicely closed. Whereas on the right side, where there's no NAD and it can't activate the sirtuin, now the permeability pore is unopposed and it can open up and lead to apoptosis. Now, nicotinamide is a very inexpensive drug. Vitamin. It's an inexpensive vitamin, and it has profound mitochondrial effects in energy. And I really recommend that you all look at the Cell 2000 by Belenky, who was able to show that nicotinamide increased sirtuin levels and shifted this ratio back towards the longevity side, improving lifespan. But this is just another easy, manipulable step that we can take to protect the mitochondria. Beetroot. Beetroot is a great source of nitrates, and nitrates prevent the leakage of protons out of the intermembrane space. So what happens is it downregulates proteins that are leakage areas for protons. And so nitrates protect the protons and the proton motor force in the intermembrane space and increases the ATP production. Nitrates have also been shown to enhance the oxidative phosphorylation and also enhance electron flux. It lowers the cost of energy. And the studies show that the effects can be felt within 1 hour. And supposedly this was one of the secret formulas by one of the English Premier League soccer teams 2 years ago who won the championship. And they said they use beetroot juice as part of their preparation for games so as to increase energy levels and speed up recovery. So this is another very simple, inexpensive, practical, evidence-based mitochondrial tonic. Acetyl-L-carnitine, this is a very important amino acid. It's critical for ATP production because it facilitates the transport of long-chain fatty acids into the mitochondria. And these long-chain fatty acids are the preferred fuel for mitochondria. Acetyl-L-carnitine has also been shown to stimulate the synthesis of phospholipid membranes. And as we age, the acetyl-L-carnitine levels decrease. And there is a study that shows that centenarians, people who were over 100 years of age, who were supplemented with 2 grams of acetyl-L-carnitine, showed increased energy, reduced fatigue, and improvement in their mental performance. Another simple area is melatonin. Paradis, in the Journal of Neurochemistry, he was doing a study on Alzheimer's patients who had difficulty sleeping. It was Alzheimer's and dementia really screws up the sleep architecture. But he found that melatonin was able to penetrate through the subcellular organelles, and especially the mitochondria, and it had great antioxidant abilities. And what it did, this mechanism, is it desensitized those permeability pores to open. So they remained closed, and it protected the cardiolipin from peroxidation and was able to rescue mitochondria. And this was a very simple, basically a very simple hormone-like vitamin that we can take. And I'm sure you're all, after all your traveling, you're all very familiar with melatonin. But another area of malleability. Caloric restriction and fasting, also known as CRIF, continues to amaze us how the body goes about repairing itself during starvation. And Wolf and his group showed that caloric restriction and fasting reduces the ROS free radical generation, which makes sense, right? Because we now have less substrate to burn to generate the ROS free radicals. It was shown to reduce mitochondrial dysfunction, and it stimulated sirtuin activity to induce longevity and repair. Caloric restriction boosts PGC1 alpha, which we all now know is the master regulator of mitochondrial biogenesis. It increases the antioxidant gene expression, NRF2, and it modulates inflammation. And it also regulates DNA repair. So all the DNA polymerases, isomerases, topoisomerases, they all kick into action after fasting. And really, there's so many different plans of fasting. It really is. It only takes 12 hours before these type of mechanisms kick in. So 12 hours of fasting. And despite the growing incidence of obesity in the United States, this is becoming very trendy in the affluent area of the United States, is intermittent fasting. Probably the cheapest and arguably the best strategy to protect mitochondria is exercise, and in particular, endurance exercises, because endurance exercises have been proven to be the best stimulus for mitochondrial synthesis. And so the more mitochondria we have, the more ATP we have. And even in the face of aging where our mitochondria are declining, exercise still stimulates multiple beneficial pathways that help our mitochondria. And so, in summary, mitochondrial function basically is the key way for the key strategy or the key thing that we should pay attention to for longevity and an increased lifespan. And now we know that there are simple areas of malleability that each of us can implement tomorrow to improve and boost our energy production and improve our mitochondrial function. I want to thank you for your attention, and I hope this was of value to you. Thank you very much.